7 minutes late. Okay. Start from current slide. Well, I just had it, and now it's gone away again. Okay. All right. Let's go over where we are, what we're doing, where we're going to wind up. Okay. Today we're in Chapter 8, and we are, I can't remember now. I'd say at least a third of the way through Chapter 8. Okay? Maybe a little further, but I do think we'll be able to finish today or come awfully close to it. All right. When we finish this, the next thing we've got is, okay, if we can finish this in 2 hours, then we can do the lab in the next 2 hours. And then you can have your test on Chapter 6 in the last 30 minutes. Don't know for sure if we'll finish this in 2 hours. If not, we may just forego the lab today and do the lab on Tuesday. Okay? And just go on and do the test. And then, I'm sorry if we're a little early, y'all may have to go early. Sorry. But get over it. Okay. Now, let me just give you the rest of my schedule. I'll be here till 6 or later this evening. I've got enough papers to grade to keep me going for the next 3 years, I think. Tomorrow I'll be on the Birmingham campus, at least in the morning, probably into the afternoon. But I do know we have a meeting, and the last I heard, I thought it was around 10 or 10:30, something in that time frame. So I'll only be available, say, from 7:45 until around 10-ish or so. After that, you'll need to, I don't know how long the meeting's going to go. Unfortunately, they go usually way too long, and there may even be more than one meeting back to back. So I probably won't be very available for the rest of the day tomorrow. Okay? Monday. Okay, Monday is, for full-term classes, is finals week. For mini-term classes, it's the last day of class, then finals. Okay? So for Monday, I don't have my classes at the class at 9:30 that I normally do. They have a take-home final, so they're going to be turning that in anytime there. So from 7:45 in the morning until 2 o'clock, I'm free in the office, and you can catch me if you need me for anything there. Second? Okay, down at 265. You know where the orientation classroom is? Right across the hall from that. Last office before you hit the stairwell. Justin Struthers is here. Okay. All right. So Monday, 7:45 until 2. I'm going to be giving an exam at 2 o'clock in this room, and it's supposed to go until 3:50. It probably will, I won't, because I've got a class, another second mini-term class, that will be, I have to go to on the Birmingham East campus. It starts at 4. So I'm going to have to leave here about 3:15, though Dr. Bryant has agreed to proctor the test for me. So they'll be in here taking their test Monday afternoon while I'm driving over and teaching my last physics class over there. Okay? So that's Monday pretty much covered. Tuesday, I'll be in this room from 8 to 9:50 or so, giving an exam Tuesday morning. Then from that time until the time that our class meets, I'm free. So you can come see me if you have anything turn in or anything to make up then. So that's basically 10 o'clock until 1:15. Now, at 1:15, we'll have this class. Okay? Now, right now, what I foresee, hope I'm right on this, is what we'll have to do is the lab for Chapter 8, the test for Chapter 8, and then the final exam. Okay. I don't think that's going to take you all more than, the lab will not take you 2 hours, I don't think. The 2 tests will not take more than 30 minutes each. So, in cheating you out of your tuition dollars that badly, what do you say of having pizza? Would that be all right? Yeah. Okay. So at 1:15, is that not too late for your lunch periods? Okay. All right. Well, then let's just figure on that. Shanika's here. All right. All right, good deal. Thank you. All right. So, do any of you have any dietary restrictions, as in the meats or the other things that you can or cannot eat? Okay. All right. Were there any restrictions, or that's going on here? All right. Any preference on the types of pizza? I'm probably going to get it from Little Caesars. That's the closest place. Maybe not the best in the world, but pretty good pizza. Any preferences? Okay. A class this size, I think we're now down to 22 students. A lot of you male. Okay. How many pizzas would you say that would be?
10, 15.
Okay. Any other guesses? 5, you think? Okay. Is that going to be enough?
6 to be on the safe side.
6 to be on the safe side. Okay. 6 pizzas. Do you have any preferences on what variety? Any of you? Meat? Did I hear that?
Yeah.
Okay. I think Little Caesars has what they call 3 meat pizza. Is that? What's that? Okay. 3 meat pepperoni. Huh? 3 meat pepperoni. What else? Sausage. Any other?
You get 3 more at the same time.
Okay, I'll get 2 each.
Yep.
3 meat, pepperoni, and sausage. Everybody okay with that? Okay. All right, we got the important stuff done. Now let's get to the trivial. Okay. So then after the pizza, we'll do the lab. After the lab, you'll do your test on Chapter 8. And after the test on Chapter 8, you'll do the final exam. Okay? And the reason we got to crowd, well, you don't have to crowd it in on those all on Tuesday if you don't want to. If any of you feel like that's too much, I'll be here all day Wednesday from 7:45 in the morning till 6 in the evening. If you want to come and finish up any 1, 2, or 3 parts of that, you can. I'll be not in this classroom, down in my office or somewhere close by. And here's why. Travis was asking about the trip. It's Thursday and Friday. So that's why I can't let you take your test on Thursday. I won't be here. Okay. So you'll need to take it either Tuesday or Wednesday. Sorry about that. Now, if you really need to get to me on Thursday, if you go to the Birmingham campus between 7:45 and 10 o'clock, because that's when I heard we were going to be leaving, somewhere around 10, you can catch me there if you need to submit something last minute or something like that. Then catch me on the Birmingham campus between 7:45 and 10. If you can't make that and you do need to turn something in, then my office is 265. Come to Bessemer campus and slide it under my door. When I come back Monday morning, because we're not going to get back Friday until 10 o'clock at night is what they're estimating. Sounds like fun to me. So I'll come back to the office here Monday morning and I'll pick up whatever's under the door. So that's the last shot. If you can't get it to me on the Bessemer campus by the end of business Wednesday, which is 6 o'clock basically, or somewhere thereabout, Miranda's here, or get it to me on the Birmingham campus before 10 o'clock on Thursday, then slide it under my door, and I'll pick it up Monday at when I get in 7:45. Okay. Now, as far as I know, grades are either due Monday at noon or Tuesday at noon. I'm hoping it's Tuesday at noon, because if there's a lot of stuff under my door Monday morning, I'm going to have a hard time getting all that graded and everything in Blackboard and on the system before noon. So I'm hoping it's Tuesday. Okay? Any questions? Now, let's just review a few other things. The research papers, I've gotten several in today. Thank you very much. The rest of them, in fact, they're all due today. That's right. No, they're due Tuesday. Okay? So, research papers, if you don't have them in today, I need them by Tuesday. Okay? Also, any of your labs, tests, and other things, if you're behind, I need them by Tuesday. Because the first thing I'm going to do before pizza, well, maybe after pizza, is pass out all the old work that I haven't passed out already. I've given you some of it, but some of it, there's one person missing this or that or the other. So get everything caught up by Tuesday. Okay? And then you'll have plenty of time to do any last minute things on Tuesday, and you also have Wednesday. But you don't have Thursday unless you really don't have Thursday either. So get it all in to me as soon as possible. All right. Did I ask this question? Have you done the student course evaluations?
Yes.
Yes, everybody? For being good, okay? And good, no. Points are for physical science, okay? But please do them because it is important to the school. It's important to me as an instructor and to the others. And then you're asked to do some other things that those people don't get to talk with you every day or every other day, so they don't have any feedback like I generally feel like I do. All right, other things. Okay, that's all I can think of right now. Any questions on how we're going to wrap up the term or any questions on physical science? Okay. Now, okay. Where we left off last time, we were talking about the atomic spectra. I think we went through most of this slide, and we got down to the last bullet here, the illustration, of the Balmer series, the hydrogen lines, okay? We talked about this. Is somebody else coming in? No? Okay. And I don't think this was hydrogen here. It might be. We'll take a look at it in a minute. And unfortunately, it's not on the slide set, but it is in the book. So this is there. Okay. I knew once I got started, I'd have to sit down again. Okay. Here's whole. And here's will. Okay. Sorry to have to keep repeating this, but I want everybody to hear. Student course evaluations done? Okay, please do those before the end of the term. Okay. And by the way, hopefully you realize this, and but I'm going to say it anyway just to make sure you know. If I can find where my book ends in the pile again. Okay. There's no way that myself or any other instructor will ever know what you put on the student course evaluation. We can't. It is impossible. Okay? What we see is a composite. They don't even let us see anything until a certain number of students have done it, so there's already an average. No way you can tell who put what. So please don't worry about that. Be very honest when you do the student course evaluation. Okay? Now what we can tell is who's done it or not. We can't tell what you put down, but we can tell who has completed or not. And I have heard, and I don't abide by this, but I have heard the dean say before, you ought to, someone asked about giving points. They were talking about marking down for people who don't turn in student course evaluations, or in other words, making you do your student course evaluation. I don't think that's academic freedom or anything. I'm asking you to please do the student course evaluation, and that's why I don't try to bribe you or anything else. Just please do them. I mean, it's part of the course. Please get that done. Okay? So don't worry about what we're going to see. We can't see anything. All right? Except who's done it and who hasn't. And we see composite scores only when they average over everything. All right, so what we got here, say in 1885, a Swiss mathematician or mathematics teacher, sounds like a good guy to me, J.J. Balmer, was studying the regularity of the spacing of the hydrogen line spectra, and he came up with a mathematical equation, and this is called the Balmer equation, and it's this. Okay, here's Coco. Okay. All right, Coco's good. Now, so let me start over. Sorry about this, folks. Y'all are going to hear it several times every time someone else comes in. Have you done the student course evaluation? Good, excellent. All right, the other things I forgot to go over, this was the two you just came in, so I'll try to make these as quickly as possible. Okay, today we're finishing Chapter 8, hopefully. I don't think we'll have time for the lab for Chapter 8, but we'll see. And we're having the test on Chapter 6. Okay? I'll be here till after 6 today, whether that takes that long or not. I'll be here trying to grade this pile of papers. Okay. Now, tomorrow I'm on the Birmingham campus from 7:45 most of the morning, probably more than the morning, into the afternoon. But I do believe we have some type of meeting, I think around 10 o'clock or so. So if you're trying to get in touch with me, try to get to me before 10. Now, we may have more than one meeting. If we do, unfortunately, I may be out more than that. But I'll try to be in the office between 7:45 and 10. And then I think the meeting is 10 to 10:30, something like that. And it'll probably go most of the rest of the day. Okay? There may even be more than one meeting. Okay. Now, that's tomorrow. Monday, final exam starts for full-term people, but you mini-term people, we still have classes. So I will be free from Monday morning, 7:45, until 2 o'clock, and that's when my first final is. 2 o'clock Monday. I won't even get to finish giving the final. Dr. Bryant is going to come in and proctor it because I have to leave at 3:15 to head over to Birmingham and teach my other second mini-term class, their last class, at 4 o'clock on the Birmingham East Campus. Okay, I'll be there until around after 6. And after 6, then on Tuesday, I have an exam here, Tuesday morning at 8. That will go approximately 8 to 10. So you can catch me here in the classroom. But then from basically 10 o'clock until our class starts at 1:15, I'll be back in the office. So you can catch me then. Okay? Then we have class. Now, here's what the class decided. I wish Coco were here to hear it because that's why I started it over. Y'all have decided that we'll start at 1:15 and have pizza. Okay? Then we will have the lab for Chapter 8. That probably won't take you a full 2 hours. I don't think it will. Then we'll have the test on Chapter 8. That won't take you, I don't think, 30 minutes. You can have more time if you need it. And then we'll have the final exam if you choose to take it. Okay? You've got to take it at some time, but if you don't like 2 tests in one day and you want to come back Wednesday, you can do that. So I'll be here till at least 6 on Tuesday. Okay? Y'all will probably be long gone before then, but I'll be here at least till 6. Then on Wednesday, I'm free from 7:45 in the morning until 6 in the evening. I don't have any final schedule. I don't have anything else. I'll be grading papers like crazy. That's anytime. If you need to come in and make up something, take that final exam, take that last chapter test, whatever you need to do, I'll be probably down in my office or somewhere close to my office all day on Wednesday. Thursday, I will not be on Bessemer. So anything you're going to turn in to me and get it to me, you've got to get it to me by Wednesday. Okay? Thursday morning, I'll be on the Birmingham campus from about 7:45 until around 10 or so. That's when we leave to go to Tallahassee for the worthless trip, okay? So I will be there the rest of Thursday or on the way Thursday and Friday and coming back late Friday. So I won't be back on either campus except to get in my car and go home. That'll be Birmingham campus. So anything that you need to turn in after 10 o'clock on Thursday, and you don't catch me on the Birmingham West Campus, come here, slide it under my door, room 265. That's where it needs to go. If it's not there, I probably won't see it. So when I come in Monday, I'll finish upgrading whatever is there. Any questions? Okay. So let's start back. Balmer, here's what he came up with. A purely mathematical formulation. He had to be a pretty good mathematician to come up with it. Here's what he came up with. I can't get my pen to operate. Well, boy, this thing is going weird today. All it allows is a laser pointer. Okay? I do not know what's going on with this device today. That's all it's allowing. I've never had this happen before. Okay. What I think I'm going to have to do is shut down. I don't know which one to shut down. Blackboard. Let's try doing the PowerPoint first. I think I saw what the problem was, but it's too late. Okay. Let's try it again. Okay. For some reason, when Blackboard, you have to have enable editing, and it wasn't allowing me to do that. Okay, let's see. Let me try this one more time. Okay. Oh. Slideshow. Current slide. Yes. That must have been the issue. All right. Sorry about this. Here is Balmer's equation. 1 over lambda, where lambda is the wavelength of the spectra, the line spectra, is equal to R, and we haven't talked about that. It's a constant. It actually has a name. Let me see if I can find it for you. 1.097. No, they don't have it in front of the book. I thought they did. But it's a constant. I don't think it's Rydberg's constant. It's one of those constants. And that is times 1 over 2 squared minus 1 over n squared. Okay? Where R is a constant of 1.097 times 10 to the 7th per meter, okay? Just per meters, okay? Now, let's go back just to see. I don't think this will work, but let me just go see. Blue, green, yeah. Actually, I think that is supposed to be the spectra, okay? Now, what they have here, they just haven't drawn it in all the way. This is supposed to be a violet line here, This would be the violet, and then the next violet would be the one above that, and that does look violet. The one above that is blue-green, and it kind of looks that way, and the one above that is the red spectrum. So this is supposed to be the hydrogen spectrum. They just didn't have this colored in properly. That's the Balmer series hydrogen line. Well, that's what he was studying. He figured out their wavelengths, developed this formula, which is a really squirrely formula to come up with, but it works like a champ. Okay? Those 4 lines became known as the Balmer series because they fit his model to a T. Okay? Now, what are those N's? Okay? The N, okay. I wish they had this diagram on the slide set, but they don't. So I'll try to just show it to you here, and I think you'll see it again. But in fact, I know you will. Okay, this is what it comes down to. This is called the ground state, the lowest energy level of hydrogen atom. Now, this is drawn for, well, this is hydrogen, okay? So that's the ground state. Most of the electrons are up here they could be in ground state or number 2. But most of the time they don't come down to ground state. There's just one little shell of electrons there. They don't, that's really not included. Most of the time they reside here. If they get energized, then they'll jump up to level 3, or to level 4, or to level 5, or really energized they go up to level 6. They're not stable up there. They don't stay there. So once the excitement is over, then they fall back to the ground state. And that's why it's 1 over 2 squared. If you remember the formula, that first, see, it's 1 over 2 squared. That's the level they're coming back to. But they went up to the N level. And it could have been 3, 4, 5, or 6. Okay? And that's where that comes from. Okay? Now, if they just went up to 3 and came back down, that's going to be the red spectrum. Very low frequency. I mean, not very low. Relatively low frequency. If it went up to 4, came back down, that's a higher frequency, 6.2 times 10 to the 14. The 2 violets, the one violet is 6.9, the other 7.3. And you get those from Balmer's formula. Now, this is showing a different formula, but it still works for both of them. Okay? So Balmer's formula, surprisingly enough, just based on mathematics alone, he was able to predict these energy levels, where N could either be 3, 4, 5, or 6. And those 4 lines became known as the Balmer series. Okay? Now, there are many other series out there. There's infrared for hydrogen. There's ultraviolet for hydrogen. There's all sorts of series out there. Those were the most easily recognizable of the visible light. Okay? Now, example 8.3, the whole reason I was doing this, example 8.3 is a problem using that. It says, calculate the wavelength of the violet line when N is equal to 6. So we're going to have N equal 6. Okay? In the hydrogen line spectra according to Balmer's equation. Okay? So, we're looking for lambda. 1 over lambda is equal to, and by the way, the lambda, are you familiar with that symbol? That's a Greek lowercase, what corresponds to our L, that's their lambda. Uppercase looks sort of like it, but this is the lowercase lambda. Greek alphabet has upper and lowercase just like we do. Okay? So we're looking for lambda in all the wrong places. No. Is equal to R 1.097. And here's Courtney. Okay. All right, sorry, we've got to take time out and go through this again because we want to make sure everybody hears it. Okay? Have you done student course evaluation? Good, thank you. Number 2, today what we're going to do is finish Chapter 8, if I can ever get all the way through it. then we're going to have our test on Chapter 6. Okay? Tomorrow I'll be on Birmingham campus, 7:45 to somewhere around 10-ish. Well, I'll be there all morning, but we got meetings, I think, starting 10 or 10:30, sometime like that. So I'll be out of pocket. So if you want to catch me early on Birmingham campus tomorrow. I'll be there sometime into the early afternoon. Okay? Monday starts final exams for full-term classes, but for mini-term classes, we still have class. So Monday, I have no finals or anything else from 8 in the morning until 2 in the afternoon. So you can catch me then anytime. I'll be down in my office or somewhere around my office. 2 o'clock, I'll be giving a final right up here, okay, in this room. It's supposed to go to 3:50. I have to leave by 3:15, so I've got someone else to come in and proctor because I'm teaching my other second mini-term class on the Birmingham East Campus at 4 o'clock. So I have to get over there and teach the class. I'll be there until after 6. Thursday, I've got a final in here at 8 o'clock in the morning, and that'll go until close to 10. After 10 and until this class starts at 1:15, I'll be in my office, so you can catch me there. From 1:15, we'll meet here, and the class decided pizza, okay? So we're going to have about 6 pizzas, 3 meat, pepperoni, and sausage, unless someone has some objection to those. Those are the 3 the rest of the class decided on. Is that okay? We'll have 2 each, so there should be plenty of pizza. So that will be 1:15. Then after that, we'll do the lab for Chapter 8, and then we'll do the test on Chapter 8, and then you'll do your final exam if you want to do them all on Tuesday. You don't have to, but you can if you want to. At least the lab and preferably the test on Chapter 8. But I will not be here Thursday. So therefore, if you don't want to do both tests on Tuesday, you'll need to do it on Wednesday. Wednesday, I'll be here from 7:45 in the morning until 8 o'clock in the evening. 6 o'clock in the evening. I'm not going to be here till late. 6 o'clock in the evening. So please, if you don't want to finish your final on Tuesday, plan to take it sometime Wednesday. I'll be here all day, 7:45 till 6. Okay? Then Thursday morning, if you did want to catch me for something, I'll be on the Birmingham campus from 7:45 until around 10, because at 10 we leave to go to Tallahassee. We're taking the school van. What a joy. Okay? And we'll be there. We'll be driving down there on Thursday. We have our meetings down there on Friday morning, and we'll be coming back and get back late on Friday. So if you have anything to turn in after 10 o'clock on Thursday on the Birmingham campus, don't take it there. Bring it here to Bessemer. Slide it under my door. 265. Okay? Any questions? All right. We were doing Balmer's series, example 8.3, calculating the wavelength of the violet line, n equals 6, for the hydrogen line spectra according to Balmer's equation. So it's 1.97 times 0.97 times 10 to the 7th per meter times, seems like that should be per meter squared, but maybe not. We'll see. Okay. No, these are just numbers. 2 squared minus 1 over, and since the n is 6, 6 squared would be 36. Okay? So 1 over lambda is equal to 1.097 times 10 to the 7th per meter. And this will be 1/4 minus 1/36. Okay? Now, what's the common denominator between 4 and 36? Common denominator between 4 and 36? 36. How many 36 is 1/4? 9. Right? Now we'll go into 36 4 times, right? So that'll be 9/36. Okay, let me see if I can get this to erase. Okay, 9/36. All right. So that gives us 1 over lambda equal 1.097 times 10 to the 7th per meter times 8 over 36, which can be written as 4 over, well, let's make it 2 over, now I'm doing 4 into it, 2 over 9, okay? Yeah, 4 over 18, 2 over 9, okay? So we reduce that. So if you'll pull out your handy-dandy calculators and do 1.097, everybody know how to do this? Sure would hate for you to miss something like this on a test if you needed it, okay? 1.097 times 10 to the minus 10 to the 7th. That would be, by the way, 1.097 EE or EXP 7 times 2 divided by 9. Okay? Now, that's going to give you a pretty good sized number. Okay? But you've got to reciprocate that, because that number you get here has to be flipped over to give you lambda. Okay? And that's where you get your lambda in meters. This is going to be very short, so you expect it to be a very small number. Anyone punched it in yet? 1.097 EE or EXP 7 times 2 divided by 9. Now, does anyone know how to reciprocate on your computer? There is a reciprocal key on most scientific calculators. Okay? I say computers, calculator. Okay? That's either a 1 over x key or it's x to the minus 1. Usually it's one of those two keys. If you can find that key, once you get this number in, flip it, and that's what you get your lambda. Has anyone done it? Okay, I see some people trying to work on it. 1.097 EE or EXP 7 times 2 divided by 9, and then once you get that done, press the 1 over x or x to the minus 1 key. That'll flip it up and give you lambda. Got it yet? Anybody? Yay or nay? Yay, excellent. Okay, we got a cheer anyway. Anyone got it? Get an answer? Somebody. You can do it on a computer if you got a calculator on your computer. Anyone got it? Can't be that hard to punch in, is it? Does anyone have it? Yes, we will be here till 6 o'clock tonight. Okay? 5:45. I thought we might be leaving earlier. Does anyone need any help with your calculator? You got one? Okay. 1.097, and then look for the EE or EXP key. You found that? EE or EXP. Depends on the calculator. If you need me to help look for it, I'll be glad to. You found it. So 1.097 EE or EXP, and you see a little other block show up. Press a 7, and that 7 should go in that block, right? Okay, you got it? Yeah. Times 2 divided by 9. Okay? Got it? Now, that gives you 1 over lambda. So do you find a key on your calculator that says either 1 over x or x to the minus 1? Okay, press that key. What do you get? Read off the number to me. Say again? Okay, wait, how many zeros after the decimal? 6 zeros after the decimal. 1, 2, 3, 4, 5, 6, 1, 4. Okay? Now, what's that? 4-1. Okay. Now, there probably are a couple more digits there. Did anyone else do it and get more digits than that? Okay. I'm surprised it didn't do it in scientific notation. It should have. But if you move the decimal 7 places to the left, that would be 4.1 times 10 to the minus 7, and then you have meters. That would be your wavelength. In the book is 4.11, okay, times 10 to the minus 7th meters. So your calculator just didn't have as many digits of precision. Or if they had done it in scientific notation, you would have had that, okay? I'm surprised it didn't because we fed the problem in. And that is what you wind up getting, that violet line on the hydrogen spectrum, the upper one, that's its wavelength. So you see, Balmer series works like a charm for hydrogen. The sad news is it was for hydrogen only. He couldn't get it to work for any of the others. But it was a start. And when we see that N, we're going to see it later. Okay? That represents something. So let's move on to Bohr's theory. Bohr, 1885 was Balmer came up with that mathematical solution, but no real reason why. Later Bohr, let's see, Niels Bohr, I believe he is, from Sweden or Denmark or somewhere like that. He came up with a theory, and here were the 3 rules in his theory. Electrons only exist in certain allowed orbits. Those were the N's, by the way. Okay? Certain allowed orbits. Within the orbit, the electron does not radiate. Doesn't give off any light. Okay? If it's staying within the orbit, it doesn't. The radiation is emitted, and this is what I was talking about, when it's absorbed when changing orbits. Now, when it goes up, it's absorbing energy, so it doesn't give off light. It's when it falls back down, that's when it gives off light. These tubes here, okay? The phosphorescent material that's inside those, when the energetic ions are moving up and down the tubes, you got a huge capacitor, they call it the ballast, and that's what's sending the charged particles up and down the tubes. When that goes past, it excites electrons, and when they fall down, they give off light, and that's how a fluorescent tube works, okay? There's nothing heating up in there except the capacitor to a certain extent, but that's not what produces the light, is when it falls off. So the radiation is emitted or absorbed when changing orbits. Emitted when it falls in orbit, absorbed when it goes up in orbit, okay? So the energy, whatever energy caused it to happen, made it jump up a level, absorbs a certain amount of energy. When it falls back down to its base, to its home orbit, then that's when a photon of specific frequency is given off. And that's why light has the spectrum of frequencies. Okay? You see the different colors. All right. Now, here's what we were just seeing. The lowest energy state is called the ground state. Okay? The higher states are your excited states. The photon energy equals the difference in those state energies. Now, they give these energies in several ways. In joules, remember, joules is a very small amount of energy anyway, but now you're going to 10 to the minus 20, 10 to the minus 19, 10 to the minus 18 joules. That's an incredibly small amount of energy, okay? They also give these in electron volts, okay? Now, if you think, can someone remind me, please, what a volt is? What is the basic units of a volt? Okay? This is one of them.
Potential difference.
It's a potential difference. And what are the units for that? Volt is the unit for potential difference. But where does a volt come from? What is its fundamental units? Joules per. What does your potential difference do? Coulomb. It gives you energy per charge. Joules per Coulomb. So if you have joules per coulomb and your electron charge is measured in coulombs, electron charge times volt, coulombs times joules per coulomb will give you joules, okay? Except these are much lower levels. This is on the energy. The E is, oh goodness, 10 to the minus 31, or something like that. Joules per electron, coulombs per electron. So that brings it down to much smaller numbers, but you don't have all those scientific notation. So this is 0.377 electron volt. Now these are negative. And by the way, all these are negative. This is the highest energy level. That's the lowest energy level. Let's see, is that right? No, this is the highest energy level. Sorry about that. Because it's negative, but a very small negative number. This is a bigger negative number. So it's less energy. Okay. And this would be negative 13.6, negative 0.377. So, another way to do this, H is another constant. That constant is it Bohr's? Doesn't seem like it. Planck's constant. Planck's constant. That's Planck's constant. He was one of the early goodness, I'm going blank on names now. Quantum mechanics came up with this constant. Max Planck, the German guy, we talked about him last time, times the frequency, that gives you the difference in your energy level. From here to here, from there to there, that's where the frequency comes from. Okay? These energy levels are the negative 13.6 divided by n squared. So there's that 1 over n squared again. So this is 1, 2, 3, 4, 5, and 6. Okay? And that's where those come from. So the lowest energy state is called the ground state. The higher the excited state, photon energy, we saw from the previous slide, equals the difference in the state energy when it falls back down, the photon's given off with that energy, and only that energy. You will not have any other energies in there. They're unique energy packets. The hydrogen atom example, here are the energy levels, there's the line spectrum. And those are the Balmer lines right there. Going from 3 to 2, 4 to 2, 5 to 2, 6 to 2. And those are hertz, they're not wavelengths. I was going to say, I don't see our number on there. Okay. So this led then to quantum mechanics, or this was part of quantum mechanics. Bohr's theory, unfortunately, worked wonderfully for hydrogen. However, it didn't do for any of the other elements, only for hydrogen. Only modeled the thin line spectrum for hydrogen. He could not figure out any way to make it be more complicated than his basic picture. Further experiments established a wave-particle duality of light and matter. Now, we always considered that energy traveled in waves, and that matter traveled in particles, okay? Here's where quantum mechanics really starts blurring the lines. They say that all waves have particle characteristics, that little photon of energy. It's not really a particle, but it acts like a particle. But material has wave-like particles, like electrons. You can diffract and diffuse electrons. They act like waves as well as acting like particles. And there was a guy, there's been several named Young. Here was one, I can't think of what his first name was. I don't even know if they mentioned in the book. Well, I can't see it right off the top. But he did a two-slit experiment producing interference patterns for both photons, which of course is light, waves. That makes sense for those to interfere. But electrons as well. They're particles. And he found out that sure enough, particles and light has wave characteristics, but also in some sense have matter or matter characteristics as well. Okay? Now, I just realized we missed example 8.4, and I know how much y'all enjoy doing your examples, so let's go back and let's see if we can find a clean slide. Let's do this one again. 8.4. Okay. An electron in a hydrogen atom jumps from the excited energy level n equal 4 to n equal 2. What is the frequency of the emitted particle? Now, really, we should go to this slide. I just don't have a lot of room to write. Okay? So you're going from n equal 4 to n equal 2. What we're looking for is the frequency of the emitted photon. Here is the formula that's going to give it to you. Okay? You do the EH, which, let's see, which one do they use? The electron volts, or do they use the other? Nope, they use the joules. So you're going from this number, that goes here, to this number, that goes there. Okay? And we know what Planck's constant is. If you don't know, I'll tell it to you. It's in the text. Thought it was somewhere in the text itself, but I don't see it there. I'm sorry. 6.63 times 10 to the negative 34 joule seconds. Very, very small number, but significant. It's in the front inside cover if you have the big text. Planck's constant is in the physical constants, second column near the center of the page. Next to the last one, or third for the last one, is Planck's constant, 6.62 times 10 to the negative 30. Well, it's funny. They put 6.62 in the front of the book and 6.63 in this problem. It doesn't really matter. That won't make a lot of difference. So let's do 6.63 times 10 to the minus 34, and that's joule seconds, times your frequency, that's what we're looking for, is equal to the difference in these energies. Okay? High minus low. Now remember, these are negative numbers. So it's negative 1.36 times 10 to the minus 19 minus a negative 5.54 times 10 to the negative 19. Okay? Now we got to do that subtraction. Well, you have a minus, that becomes a plus, and the difference between those two would then be 4.18 times 10 to the minus 19. Okay? That gives you HF. Okay? Let's divide by H to get your F. So divide this by 6.63 times 10 to the minus 34. Now this was in joules. This difference was in joules, and this is in joule seconds. Obviously the joules cancel out and you're left with per second. Does anyone know the common unit for a per second? Sometimes we call it cycles per second. You tune it on your radio. Frequency. That's what a frequency is. And what's the unit that we use for your radio? Hertz. And this will be some multiple. On the radio, it's usually kilohertz or megahertz. Or TV, either one. So, if someone's got a calculator, 4.18 EE or EXP minus 19 divided, and frankly, guess what? Oh, no, I'm sorry. Divided by 6.63 EE or EXP minus 34, and see what you get. You want to do it? 4.18 EE or EXP negative 19. And when you do a negative sign, don't do the subtraction key. Do the little negative sign that's in parentheses. That's your negation key. The other minus sign is the subtraction key. That does something different. So it's a negation key. divided by 6.63 EE or EXP, negative 34. Anyone get an answer? What you get?
6.1538 times 10 to the
Okay, so it's 6.15. A few more, huh? 38 times 10 to the 14, and that unit is hertz. Okay, let's see what they got in the books. Oh, they rounded just 6.15. Sorry about that. 6.15 hertz. And I guess the reason for that is they only had these in 2 significant digits, 3 significant digits as well. That's approximately the blue-green line of the hydrogen spectrum. All right, good deal. That we should have done while we were on that slide. I missed it, sorry. Okay. Now, continuing in quantum mechanics, here they ran into a problem, okay? Remember, I think we already addressed this problem. Well, let's move on. We won't rehash that. Louis de Broglie, okay? When I took this quantum mechanics as an undergraduate, I had 2 courses in it. Both times I wound up with this guy who had the strongest, most least understood Irish brogue I've ever heard in my life. And I remember him talking about Louis de Broglie, and I mean that R had about 3 syllables in it, okay? De Broglie, okay? Around 1923, he postulated these matter waves. Now, they had seen the results of this in Young's 2-slit experiment. You had seen that electrons exhibited characteristics of waves. Okay, they had interference patterns and things like this. So Louis de Broglie came out with a way to postulate how these happen. The wavelength was related to the momentum of the particle. Okay, anyone remember what momentum is or was? We've had it. Your final, of course, will be comprehensive, so you need to know that. What was momentum? It was Newton's quantity of motion. Mass times
Gravity.
Sorry?
Gravity?
No, that's
mass times velocity.
Mass times velocity. That's what momentum was. So the wavelength was related to that. It's related to the speed of it, but also to the mass. Matter waves in atoms are standing waves. Now, what that means, if you were to take a hose and pick it up and do this and watch it snake down the grass, that's a moving wave, not a standing wave. Now, I think I've asked this question before. Have any of you been to the McLean Science Center downtown Birmingham? Okay, if you ever get a chance, good. They have a little device over there that makes waves, and a light that shines on it, you spray little droplets of water, mist of water in there, and the light reflects off of that, and you can set up the frequency so it looks like the wave is just there fixed in place. It's really going very fast, but it's a standing wave. That's what we're talking about. Well, that's what Louis de Broglie said. The matter waves in atoms are standing waves. They have to connect, and look like a full wave constantly. And here is this illustrates this bullet here. The particle wavelength, have a wave, it has a wavelength, have wave characteristics. There's good old Planck's constant again, 6.63 times 10 to the minus 34 joule seconds, really small number, divided by mv, your momentum, the mass of that particle, and the velocity of the particle, speed of the particle. Okay? Now, for these wavelengths to make sense, the mass can't be a very large number. If the mass was very large, this thing gets incredibly small. So small, you probably aren't going to be able to detect it. The velocity has to be relatively reasonable too, okay? And the product certainly has to be. Of course, this is going to be a pretty small number to begin with, So you're going to have some very, very small wavelengths. Okay? But that's basically the formula that de Broglie came up with. All right? And here's what he meant that matter waves are standing waves. Here's a standing wave. Now, here's what we say. We say the electron is in this energy level. It really isn't, okay? Or it is, kind of. That's its average energy level. But it fluctuates as a wave about that. Sometimes higher, sometimes lower. Almost a sine wave type thing. They don't have this quite precise here on the circle. But that's what it is. If it came that it didn't have a standing wave, that's a misfit. That's not going to happen in an atom. They all have to connect like this in an atom and become a standing wave. You can't have an interfering wave within the atom. That's what we call the orbit of the electron, but it fluctuates above and below that, but it has to form a standing wave. It has to connect and always repeat that pattern. Okay? And that was what de Broglie came up with, postulated that had to be the case. Otherwise, it's unstable. It doesn't work. All right. We have another example. Let's back up and do it. We got a little room here. What is the wavelength associated with a 0.150 kilogram? What's that a measure of? 1.015 kilograms? What does that measure? Anybody? Mass, of course, that's your mass, okay, of a baseball, okay, with a velocity equal to 50 meters per second. Okay? That's a fairly small, no, that's a pretty reasonable mass. It's much smaller than our masses, but, you know, something we'd certainly be able to measure. 50 meters per second. It's going along pretty well. Pretty decent speed. Okay? What is the wavelength associated with that? Well, what was de Broglie's formula? Lambda is equal to Planck's constant h divided by your momentum. Okay? And Planck's constant was 6.63 times 10 to the minus 34 joule seconds divided by your 0.150 kilograms times 50.0 meters per second. Okay? Now, I think for units' sake here, we need to break down what a joule is. Does anyone remember what the fundamental units of a joule is? How do we get energy? Work. What was that formula? Y'all did it when you ran the stairs. How did you calculate your work? Oh boy, how long ago? Work is force times the distance. Remember? That would be forces measured in newtons times distance, Newton meter. That's what a joule is. Okay? So this would be, a joule is a Newton meter. But that's not a fundamental unit. What is a Newton? Anyone remember? Remember Newton's second law. What does it say? Force equals. And Travis started to read that one when he was looking for momentum. He actually did read it, but he had the wrong thing there. What is a Newton? Mass times. Force is equal to mass times. Oh, but that was 3-4 chapters ago. We don't need to know that anymore, do we? All this stuff ties together and builds together. A newton is a force times an acceleration. Y'all have done it several times in the course. Kilogram meter per second squared. So here we have a kilogram meter times meter would be meter squared per second squared. So that's what we have, kilogram meter squared per second squared. Well, this kilogram will cancel out that kilogram. This meter will cancel out one of those meters. That second will cancel out one of those seconds. Okay? And what you're left with is meters. Okay? Because then this second cancels out the other second. Okay? So you're left with meters, and that's what we're going to measure our wavelength in. A length is measured in meters. So now what we got to do is the numbers. 6.63 EE or EXP, negative 37. Be sure you use that minus key in parentheses. Divided by 0.150, divided again by 50. Anyone get it? 8.84. And it's got some enormously small exponent, times 10 to the negative 35 meters. Okay? Now, I don't know if you've ever gone decimal places negative 35. That would be 0.000000000. That would be almost 12 of those sets of that. 884 would be the last 4 of that. That's an incredibly small number. You're not going to be able to measure that frequently with anything we've got. 8.84 times 10 to the minus 35th meters. 8.6 is also down there. What is the wavelength associated with an electron of a velocity of 6 times 10 to the minus positive 6 meters per second? So let's change our problem here. I'm going to try to keep as much as I can. The electron mass differs. The electron velocity differs. Okay? And everything else will be okay. Planck's constant's the same. And okay. So what we'll need to look to the front of the book or somewhere where you have the table. Electron mass. Nope. Electron rest mass. 9.11 times 10 to the negative 31 kilograms. 9.11 times 10 to the negative 31 kilograms. Okay? And we were told its speed is 6.00 times 10 to the 6 meters per second. 6.00 times 10 to the 6 meters per second. That's 1,000,000 meters per second. No, I'm sorry. 6 million meters per second. Okay? That's moving. Moving. Okay? Now, pull out your handy dandy calculators. Let's do it again. This time you see you have much more extreme numbers here. 6.63 EE or EXP negative 34 divided by 9.11 EE or EXP negative 31. And that answer you divide by 6 EE or EXP 6. Press the equal sign and what do you get this time? Anyone pressing? 1.21 times 10 to the negative what? 2? 10. 10 to the negative 10. Whereas before we were 10 to the negative 32. So this is far more reasonable. Okay? That wavelength, you can deal with. Okay? Still very small. But let's see. You have this on the next page. 1.21 times 10 to the negative 10 meters. Perfect. Okay. Now, Now we move to wave mechanics. Okay? Now all sorts of weird things are going on here. And by the way, if quantum mechanics seems a little mysterious to you, don't feel like the Long Ranger. I mean, I think some of the greatest minds that ever lived, it still feels strange to them because it's not something that's really all that intuitive. When you start having to deal with waves, you have to come up with things like probabilities and stuff. Where is it really listed? Well, these wave mechanics were developed by Erwin. I was thinking it was Edwin, but I guess it's Erwin Schrödinger. Boy, the equation he came up with, Schrödinger's wave equation, it's a monster. Okay, I'm not even going to write it down. I don't think I could even remember it, and it's not in your text. It treats atoms as a three-dimensional system of waves, X, Y, and Z, because it fills up space. Atoms are three-dimensional systems of waves. It contains successful ideas of Bohr's model and so much more. It describes the hydrogen atom and higher level atoms. See, hydrogen atom only has one electron, so it's a little bit easier to keep track with it. When you get more than one, Bohr's model fell apart. Balmer's series didn't work. But Schrödinger's wave equation did work. Okay? It forms our fundamental understanding of chemistry, even though it's here in physics. So we're in the chemistry chapter now. So, but Schrödinger was considered to be quite a physicist, more so than a chemist, but he contributed big time to chemistry. So here's the quantum mechanics model of what's going on. The quantum numbers specify electronic quantum states. Oh boy, that says a lot, doesn't it? What you can think of when you see quantum states, think energy levels, like we've been talking about before. Here's the visualization, though it's not particularly keen to me. Wave functions and probability distributions. Okay? Let's say this is hydrogen. Hydrogen doesn't have that many electrons. You know it doesn't. But these are the possible or probable locations of those electrons. That electron, that one electron. Okay? It could be way out there, but most of the time it's in closer. So if you want 90% probability, you can close in on that. You know, these outliers you're going to do away with. So that's a lot more reasonable. But we still don't know exactly where it is. It's somewhere in there. Okay? And basically what this is saying, the electrons are delocalized. You can never tell exactly where it is. Okay? Just can't. You can just say where it most probably is. Okay? And you have to live with that. Now there was I don't know if you call it conjecture or kind of a physics joke on Schrödinger's cat. Is Schrödinger's cat really there, or is it just probably there? Okay, that came into the probability. There's a chance it really wasn't there, though you thought you saw it there, because just like here, you don't know exactly where that electron is. All you know is where its high probability is. It's not anything that's easy to describe. Okay? So here comes these quantum numbers and electrons. And you might say, my word, why does this matter? Well, if you'll hang with me for a bit, you'll see when you look at the periodic table, this matters big time. Okay? So let's talk about these four quantum numbers. The principal quantum number is your basic energy level. Okay? The energy level of that electron. That has to do with the average distance from the nucleus. The highest energy levels are the lowest or closer, the higher is further away. Okay? That's your basic quantum number, principal quantum number, N. Then you have another quantum number, and I don't know if you remember when we were doing the rolling the balls down the track, the momentum experiment. I said one of the things that's messing up the results here is that the balls are spinning as well. That gave them angular momentum. Well, here the angular momentum comes into play. There is another angular momentum quantum number called I. Not L. L. N is the principal quantum number. That's the principal energy level. Then after that is L, which is the angular momentum quantum number. That leads to your spatial distribution. And these numbers are 1, 2, 3, 4, 5, 6, 7. Technically, they go higher. We'll see this later. We don't go past 7. This one has letters. S, P, D, F, G, H. We never get to G and H. We only deal with S, P, D, and F. Now, who picked out these letters, I don't know. After F, which we never use, they follow the alphabet. But the first ones that we do use, they just sort of seem to be fairly random. But these are your angular momentum quantum numbers. They're not really numbers, they're letters, okay, but they correspond to a angular momentum number, which is how much angular momentum it has. The next level is your magnetic quantum number. It's a spatial orientation of the orbit, not just of the electron, but of the orbit. And we'll see pictures of this later, so don't worry about it yet. Magnetic quantum number. And then the final one is your spin quantum number. And that's your spin orientation. And basically there's two. There's spin up and spin down. Okay? Usually that's labeled as plus 1/2 and minus 1/2. Those are your two spin quantum numbers. The magnetic quantum number, notice they don't give anything about it. We'll see in a minute what's going on with it. Okay? And again, it has to do with the orientation of the orbit. Okay? Now, the energy levels is just how far away you are from the nucleus. And you get those numbers 1, 2, 3, 4, 5, 6, 7. They're not measuring anything, they're just naming those levels. Okay? The angular momentum quantum number is a spatial distribution, and your s orbitals are always the lowest of these. They're always sort of spherical. Okay? The p quantum numbers are kind of barbell shaped. Okay? This would be on the x-axis, that would be on the y-axis, it would be on the z-axis. So you could have 3 p orbitals, x, y, z, you might say. 1 s orbital for every n. Okay? 1 s and 3 different p's. Okay? Hang on to that concept. All right? These would be your 3 p's. Along the x-axis, along the y-axis, and along the z-axis. But all those are p orbitals. You have 3 different ones of them. Okay? 1 s for each energy level, and 3 p's for each energy level. Okay? We're going to see that a little bit later. Okay? Now, again, they're skipping your magnetic quantum number, not showing you anything about it. Here's the spin quantum number. If you can imagine that an electron would be a little ball like that, they're way too tiny to see. We don't know what they really look like. But if they're spinning this way, they spin up. Spinning that way is spin down. Right-hand rule. Okay? And that would be, usually they give this as plus 1/2, that minus 1/2. But you don't need to know that now. Just that there are 2, 1 up and 1 down. Okay. Now, your first level, n equal 1, first energy level, how far away you are from the nucleus. When n is equal to 1, you only have one sublevel, and that's s. Okay? And that s only has 2 possible electrons. Hydrogen has 1, helium has 2. Lithium on the second level, only 1 in the second level. Beryllium has 2. So it can only have 2. So the maximum number of electrons per main energy level is 2 there. When you go up to the next energy level, where n is equal to 2, you have 2 different sublevels, s and p. Okay? Now the s can have 2, spin up and spin down. The p, remember, there's 3 orientations for p. There's x-axis, y-axis, and z-axis. Okay? Each one can have 2, so that's 2, 4, 6. So the total number of electrons in the 2p is 6. And when you add the 2 and the 6, you get a total of 8 electrons in the second energy level. And we'll see this as an important thing in your periodic table. When you go up to the third energy level, you can have 2 electrons in the S, 3 in the P's, and the D's. Okay, now we didn't see a picture of D. I think maybe one in the book. The D's then fill in the gaps between the other two, between these 3, and you can get up to 10. Now, that seems a little bizarre, but let me kind of explain to you. Think of your odd integers. 1, 3, 5, 7. Double that and you get your 10, 2, 6, 10, and 14. The reason you double is because you spin up and spin down. Okay? So that's where these numbers come from. Okay? And so when you get up to n equal 4, you can have 2 in the S level, that's all. 6 in the P level, 1, 2 in each X, Y, and Z. 10, you got 5 different D's with 2 electrons at each, so that's 10. 7 different F's with 2 electrons each, that's 14. So here in n equal 3, you got 10, and 8 is 18. N equal 4, you can have up to 24, 30, 32. Okay. That's the max you can have in that energy level. All right. Now, oh yeah, here's in the book. I don't think you're going to see this on the slide, but on page 217, you see the s orbitals, the p orbitals, the d orbitals are so complicated looking you can hardly make them out. Okay? And basically, the energy sublevel, PD, SP, D, or F, the magnetic quantum number then gives you how many possibilities you have there, how many orientation. That's where the 1, 3, and 5, and 7 came from. And then put together, that gives you those numbers. That's a pretty lousy way of trying to explain it, but that's what you come up with. So let's look at these electron configurations now. Actually, before we get there, there was an important thing to do, and I thought they were going to have it on the slide, but they didn't. Okay? I guess I'll put it in here. Let me put it here, maybe. Every electron can have only one unique set of these numbers, okay? And you can't have 2 electrons with the same set of numbers. So this first one, only 2 electrons there, 1 spin up and 1 spin down. N equal 1, sub-energy level S, spin up, spin down. Okay, unique. N equal 2, 2 of those electrons are S, 1 spin up, 1 spin down. There's a P on the X, a P on the Y, a P on the Z. Each has 2 electrons, 1 spin up, 1 spin down. That's where those 6 come from. You can't have 2 electrons with everything identical. They're going to have something different. Either N level, the L number, the M number, or the spin number. Something's going to be different. So that's where those come from. That principle was developed by Wolfgang Pauli, an Australian physicist. His summary, now known as the Pauli exclusion principle, states that no 2 electrons in an atom can have the same 4 quantum numbers. N, L, I think the magnetic is M and S, okay? You just can't do it. Okay, so now let's look at these electron configurations. I can see y'all are, oh wait, I didn't see Gary come in. You need to tell me these things so I'll mark you present. Okay, but Gary's here. Does anyone else come in that I didn't see? We're missing Josh and Lauren. Okay? All right, since you came in, Gary, sorry for you other folks that you have to hear this again. Let me just go over end of the term stuff. Number one, have you done student course evaluations?
No, I'm good.
Not yet. Okay, please do it soon rather than later. Okay? You can wait till the end of the term, but just don't forget to do it. Okay? Number two, what we're going to do. Today we're finishing Chapter 8, and when we finish Chapter 8, we'll have the test on Chapter 6. Okay? I think that's going to take up most of the day. I'll be here till 6 o'clock tonight. Hopefully y'all won't be, but we'll see. Okay? Now, tomorrow, I'm on the Birmingham campus tomorrow. If you need me for anything, that's where I'll be. And we'll be there most of the morning, maybe into the afternoon. But we have meetings in the latter part of the morning. And I don't know how many meetings and how long they're going to last, but basically probably after 10 o'clock I'm going to be hard to find. So if you need to get in touch with me, get in touch with me early in the morning, not after 10. I'm probably going to be in meetings from then on. Okay, that's tomorrow. Okay, Monday. For full-term classes, that's finals week. Starts Monday. No more classes. For mini-term classes, we have classes. Okay, so I have a mixture of both. So Monday, I have no finals, nothing from 7:45 in the morning until 2 o'clock. So you can catch me in my office or somewhere near the office all morning and early afternoon. At 2 o'clock, however, I've got a final in this room, and it's going to be close to 2 hours. I can't be here the 2 hours because I've got a class on the Birmingham East Campus starting at 4. So Dr. Bryant's going to come in and do the last part. I'll be here from 2 till 3:15 approximately. He's going to come in then. After that, I'll be off camp. I'll be on Birmingham East Campus. Okay, so that's where I'll be. Tuesday, I've got an 8 o'clock final in this room from 8 to 9:50, approximately 10 o'clock, let's say. And after that, as soon as I can get all those students finished, then I'll be moving down to my office. I'll be there until our class time. We have class on Tuesday. What we're doing in class on Tuesday is the lab for Chapter 8, and that's a paper lab. We'll do it here in the classroom. You can work together. I encourage you to do so. And the stuff we're talking about last time and today will be on that lab. Okay? In fact, especially the stuff I'm talking next. Okay? Then, but it has to do with what we just talked about. Then, after you do the lab, will be the test for Chapter 8. Okay? Because hopefully we'll finish the chapter today. And then, you'll have an option. You can go on and do the final if you want to. I forgot an important part of it. That at 1:15, before we start any of that, we're having pizza. Okay? Now, anyone who came in late have any eating restrictions? The rest of the class said no, and they wanted all meat pizzas. So we're going to have 2 free meat pizzas. These are from Little Caesars. 2 pepperoni pizzas and 2 sausage pizzas. If anyone has objection to that, I can get a cheese or something else, if you veggie or whatever else you want. Okay? Everybody okay with those? Okay, that's what we start on Tuesday. Then we have the lab. Then we have the test on Chapter 8. And then if you choose, you can go and do your final. If you don't do your final on Tuesday, you've got to do it sometime on Wednesday. And I'll be here from 7:45 in the morning until 6 o'clock in the evening. All day long, no final scheduled, so you can come in and take either of those 2 tests or anything else on Wednesday. I will not be on this campus after Wednesday. Thursday, I go to the Birmingham campus. I'll be there from 7:45 until 10 or so. Somewhere around 10 or so, we're leaving to go to Tallahassee. So you won't be able to catch me after 10 o'clock on Birmingham campus Thursday morning. If you need to drop off anything for me, like old labs or research papers or things like that, after Thursday at 10, you're going to have to slide them under my door here. Don't leave them on the Birmingham campus. Bring them here and slide them under my door at 265, just down the hall here. Okay? Then I'll be We'll be going to be coming back from Tallahassee late on Friday, so you won't be able to catch me then. And then Monday I'll be back in the office. That's when I'll grade all the rest of the things that are under my door. So try to minimize those. Get them to me beforehand if possible. I like to be grading there when I'm wasting time. When I have time. Okay. So, I think I've said that enough. Now, let's look at these electron configuration. This is 8.4, top of page 218. Electrons are arranged in, this describes the arrangement of electrons in the atomic orbitals. Now remember, we never know exactly where the electrons are, we just defy probability. So we have these quantum numbers, principal quantum number, what was that? What letter? Just had it on the slide. Principal quantum number is N. In reality, we only go through 7. 1, 2, 3, 4, 5, 6, 7. You could theoretically go higher, we don't. Angular momentum quantum number. What letter does that represent? It was on 2 slides ago. L. That's the L. And the angular momentum quantum number has to do with which energy level. Principal energy level, you only have S. Principal quantum number 1, you only have S. 2, you have S and P. 3, you have S, P, and D. 4, you have S, P, D, and F. We never go above F. Theoretically, you could. We don't. Okay? Magnetic quantum number. Now, the slide didn't show it, but I'm pretty sure that one's M. And that tells how the orientations are in the L's. Okay? That's sort of nebulous, but that's what it tells you. Okay? S, you only have one possible orientation there. P, you have 3 different orientations. D, you have 5 different orientations. F, you have 7 different orientations. Okay? So that's your M quantum number. And then your last quantum number is the spin, electron spin. That's plus 1/2, minus 1/2. That's your S quantum. Yeah, S quantum numbers. They didn't say that either, but that's what it is. Okay. Now, every unique set of those numbers specify the atom's quantum state. How many electrons does it have? That tells you know its quantum state. Oh, and here's Pauli's excusing principle. I thought it was going to be on the slide. Each electron has a unique quantum numbers. Only it can have several N's, several L's. Each electron will have only one, but several can have the same one. But you can't have the same combination, exactly the same combination of all of them. The maximum of 2 electrons per orbital, spin up, spin down. So the chemical properties are determined by that electronic structure, where these electrons are oriented in each of these atoms. This is what makes chemistry happen. So how do we write these electron configurations? Now, the electrons fill these available orbits in an order of increasing energy. But here's the thing not to be confused by. Level 1 is always less than the energy of the other. Level 2, always less than the ones below. Level 3, S and D, S and P, follow exactly what you would expect, but D doesn't start filling until you do 4S. So the shell capacities, and this is what we talked about before, S electrons only have 2, P's only 6, D's only 10, and F only 14. The easy way to remember this, odd numbers, 1, 3, 5, and 7, double that and you get this. So here's how the electron levels fill. This, I think, is going to be strontium. The strontium has 38. All I can think of is mass number. Its atomic number is 38, meaning 38 protons, so therefore it'll have 38 electrons if it's neutral. Here's how you fill. Okay? Start up here at this arrow. you fill the 1s electrons. 1 is your quantum number, your principal quantum number. S is your angular momentum quantum number. You fill 1s, you can put 2 electrons in it. Then go up to the top again and start with 2s. You can put 2 electrons in it. Go back to the top and you do 2p. You can have 6 electrons there. Okay? Then you do 3s. Okay? Everything's following like it's supposed to here. And you can put 2 more electrons there. Go back to the top and you do your 3p, just like as it should be going. And that's 6 more electrons. 4s before you do 3d. Okay? Up till now, everything was following exactly like you would expect until you get here and you do 4s before you do 3d. 4s is 2, 3d is 10. You can get up to 10 electrons there. You just fill them one at a time. Okay, then you fill the 4p and then the 5s before you go up here and do 4d and 5p and 6s. Then you go back up here and do 4f before you do 5d and you fill them like that. Then you go up here and here. So you always are following the pattern here. This is probably the most important diagram it has for doing your lab that we'll be doing next time. And basically, what you do, when you get to the bottom here, you go back to the top here. Get to the bottom here, go back to the top. Bottom here, go back to the top. Bottom here, go back to the top. So just connect these arrows. I'm making a mess of it, but this is what you do. And this is how they fill. Surprisingly enough, that's how it goes. Okay? Now, if you've ever looked at the periodic table, it probably doesn't look anything like it, but that's exactly why it's the way it is. The one in your book connects those dots. Okay? Mine is pretty poor. Okay. Your table 8.3 in your book shows the electron configuration for the first 20 elements. Hydrogen through calcium. And you'll see hydrogen is 1s1. Only 1 electron there. Helium's 1s2. 2 electrons. You filled the first energy level. That's why it's the top row in the periodic table. Only 2 elements. Hydrogen, helium. Then you come down and do 2s1. That's lithium. And then you do 2s2. That's beryllium. Then you go to the 2p's. And that picks up with boron, and then I think carbon, and you go from the, here it is, boron, carbon, nitrogen, oxygen, and fluorine. And neon. That finishes, okay, let's start. 1s1 is hydrogen, 1s2 is helium. 2s1 is, it has a 1s2 in it, and then you do 2s1 is lithium, 2s2 is beryllium. 2p1 is boron, 2p2 is carbon, 2p3 is nitrogen, 2p4 is oxygen, 2p5 is fluorine, and 2p6, that finishes, that's neon. Now look at neon. It's finished 2 levels. Well, go back to helium. Helium finished the first level. Only 2 electrons. That's all you have. Helium is a noble gas that doesn't combine with anything else. When you get here and finish neon, it's a noble gas. It doesn't combine with anything else. It doesn't share electrons. It doesn't lose electrons. It doesn't gain electrons. It's happy. It's got a full energy level. Okay? Then you come back down here with 3s1. That picks up with sodium. 3s2. That would be magnesium. Then you go back to the top. 3p1 is aluminum. 3p2 is silicon. 3p3 is phosphorus. 3p4 sulfur. 3p5 is chlorine. 3p6 argon. And you filled that energy level completely up, and that shell, not the whole energy level, but that shell completely filled. The sp, it doesn't combine with anything else. Argon is another noble gas. Then you come down and 4s1 is potassium, 4s2 is calcium. That's as far as this table goes. But your periodic table continues. Okay? Now look at, well, let's see, they're going to show this on the slide, so I'll wait till I get there. Okay, and there's the one for strontium. That's way past what this table in the book shows, but you can fill up your 1s2 because you got a total of 38 electrons. Here's 2, and 2 is 4. You have to fill them all up, and 6 would be 10, and 2 more would be 12, and 6 would be 18, and 2 more would be 20. And then you do the D's, you get fill up 10, that would be 30, 36, and 2 is 38. That's what strontium is. And look where it is on the table, right there, right underneath calcium. You fill up the first energy level, 1s, 2s, 2p, 3s, 3p, 4s, and then you start filling up the 3ds. And that's why you have this big gap in the middle, and you fill up 10 here. There's your 3D 10. And you fill those up, then you come back and do your 4p over here, and then your 5s, 2 here, and then you do the next 4d, okay? And that's that 10. And you keep going. When you finally get to the F's, where are you now? You're down here to these series. 14 there. That's where those come from. These fit right in here. The table is way too wide to get on the page. Okay? So you go from there. Okay? So you see, this is matching your periodic table to a T. Okay. There is a little thing here on firework configuration. Strontium is used a lot in fireworks because it has a beautiful bright red color, I believe it is. And flares and other things use strontium. That's one of the main uses that I know, maybe the only use I know for strontium. I'm sure it has something else. I think they use it in semiconductors some too. Okay. So here's the periodic chemical properties. This is understood in terms of your electron configuration we were just talking about. The electrons in the outer orbits determine the chemical properties that you have. So this is summarized in the periodic table, and we're going to have a picture of it in a minute. The rows are your periods, principal quantum numbers. Row 1 is principal quantum number 1, row 2, 3. They don't follow exactly that way, but pretty close. The columns are your families or groups. Your first column, your alkali metals. If you think about them, 1s, 1 electron in every one of those. Okay, so they all act the same. Alkaline earths are 2As. They're the second column. The halogens over there are 7A. They're the ones right before the noble gases. Noble gases are 8A. Those are the primary ones. The others sort of mix up some. The A group families, they're the main groups and representative elements. They all act alike. Potassium acts a lot like sodium, and all the ones that are under this. Calcium acts like magnesium. Chlorine acts like fluorine, acts like iodine, acts like, so they all act alike. And your noble gases, they don't combine with anything. And so they all act alike. Your B group then are your transition metals, elements or metals. They're basically in those F groups. They do stranger things. Okay? So let's take a look at your periodic table here. Again, your rows are your energy levels. There's your 1, energy level 1, energy level 2, energy level 3, 4, 5, 6, 7. That's why I say if you don't go past 7, you run out of elements before we get there. Okay? Then, your columns represent the thing. Hydrogen, lithium, that sodium, potassium, rubidium. Now these, the higher you get, the rarer they are, so you don't run into these much. But these act very, very similarly. They all are easy to lose an electron. They form ionic compounds. Okay? Sodium chloride, lithium chloride, potassium chloride, or fluoride, or any of the others. Level 2, they have 2 outer electrons. Okay? They sometimes lose them, sometimes share them, mostly lose. Magnesium and calcium act so similarly. Okay? Then jump over to the 7s. These are they like to gain electrons. Fluorides, bromides, iodides. You don't get into that too much. You see, that's a radioactive. Anytime you see it in parentheses, that means it's a radioactive element. You probably don't deal with that very much. And then your noble gases that don't combine with anything: helium, neon, argon, krypton, xenon, and radon. Even though it's radioactive, it's still a very non-reactive gas. Okay? Now, they didn't say that much about 3, 4, 5, and 6A. I'll tell you a little bit. You see the thing with 3, you're on a dividing line here between your metals and your non-metals. So it's sort of hard to classify. The non-metals act more alike and the metals act more alike. Okay? But these are still sort of transition metals. These form some of your semiconductors along in here. Okay? But your 6A, these form mostly covalent bonds. They don't gain 2 electrons as much as they share 2 electrons with other things over here. So that's what your 6As do. 5As, a lot of these are fairly unstable. If you think about some of your nitrogen compounds, like PNT, that the N is for nitrogen, that sort of blows up because these are in phosphorus. I don't know if anyone has ever heard the term Willie Peter. That's white phosphorus. That's what they use in bombs or markers and things like this. They really give off. They can be fairly unstable, or when they're very stable, they're so stable you can't do much with them. So these are sort of transition in here. Now the B's here are all within your F's. Remember S, the D's. These are your D's. And those are your families that are B. And just to remind you, look at 8B here. What's in that top row in the 4th row here? Iron, nickel, and cobalt. Where have we heard those 3 grouped together? Come on, it wasn't that long ago.
Magnets.
Those are your naturally occurring magnetic materials. That's all of them right there under 8B in that one row. Okay? Remember copper and silver, and even gold, what was pretty special about those?
Conductors.
Your very best conductors are right there under 1B. In that order. Well, not quite that order. Silver's best, copper's next, and gold's not far behind. Okay? 2B, I don't know too much about that. Some weird things going on there. Mercury's a liquid. What's it doing there? But it is. Okay. These others have some characteristics. Now, so you see the periodic table of that electron structure hand in hand. All right. Now, another way to classify or look at these things, now we already talked about this. Group 8 over there, noble gases, filled shells of electron, inert, they don't combine with anything, okay? Anything, ever, okay? Now, if they have 1, 2, or 3 outer electrons, that's column 1A, column 2A. And then the 3s can be sort of in several places there. They either lose electrons to become positive ions, and these are typically metals. Some of them are very soft metals, things we wouldn't think of as metals, but they are. If you have 5 to 7 outer electrons, that's over here, 5, 6, and 7, those tend to gain electrons to form negative ions. And those are typically non-metals there. And then your semiconductors are intermediate. Those are that, I said, that band down here that don't fit in either camp. Those are your semiconductors. They're something between metals and non-metals. Okay? And here's how those break down. And here's Lauren. She made it in for the first part. All right. Now we're just missing Josh. Is our own. Well, wait. Tef. Missing Josh and Tef. I'd mark that here. But so again, let's look at this now. Here's another way they sometimes represent these things. They put a dot for how many outer shell electrons they have. Hydrogen and all the group 1s here, 1As, only have one outer shell electron. Real easy to lose that electron and become a positive ion. Group 2, 2 outer shell electrons. It's not too hard for them to lose that first electron, those 2 electrons, and become ionic, electrostatically bound. Okay? When you get on over here, now they skip the P's in here, the D's in here, the P's, okay? And you pick up, these are only the A's. Boron, 3, okay? They kind of go either way. Aluminum, a metal, a fairly good conductor, rather strange here. These in the middle, 4, they can go either way. They really form covalent bonds. Carbon, silicon, germanium, tin, and lead. Okay, but these are getting heavier metals in here. Not that common. Okay, nitrogen, 5 outer electrons. Again, covalent bonds mostly. Some of these can be a little unstable, like some of the nitrogen and phosphorus. Other times they're extraordinarily stable. Okay, this is antimony, maybe. I don't remember exactly. Bismuth, way down here. 6, oxygen, sulfur, and the others are more rare. These form really strong covalent bonds. And then your group 7, these are called your halides, and these grab electrons like crazy, trying to fill their outer shell. You see, that's why these lose them, because once they lose an electron, they look like the outer shell is filled. Okay? So they're happy to lose that so they can have a filled outer shell. These love to grab electrons so they can have a filled outer shell, except they're no longer atoms, they're now ions. These would be positive ions, those would be negative ions. And these filled up, they don't combine with anything. So your reactivity, even though these are right next door to each other, these are some of the most active of your ions. These are the most inactive you have. So even though they're right next door, all depends on how close they are to filling a shell. If they're full already, they're not going to combine. Now, here's another way of looking at your periodic table. Most of your, and now with one exception, hydrogen really should go over here, okay, for this purpose. It's not a metal, okay, it never will be a metal, so it really should be over here for this illustration. These are metals. Now, these are very soft metals. You don't even think of them as metals, but they are by their nature. These are what we usually think of your metals. These are called transition metals. Iron, nickel, cobalt, vanadium, all these things are metals. These are your non-metals. Many of them are gases or very reactive solids. These are your semiconductors. They sort of have some of the characteristics of metals, but some of this. And your semiconductors, silicon, germanium, I don't think that's arsenic, I think that's actinide or something like that. Antimony, these form some of the semiconductors, and a lot of your semiconductor industry is based on doing things with that. Okay. So this shows this last slide here. Okay. Whoa! Can it be that we're at the end of the chapter? There were a few other things I probably should have pointed out as we went. Oh, here we are. On this slide, when they mention the alkali metals, this is shown in table 8.4. These are your alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium, or whatever you spell that. They all have a filled inner shell too, but the outermost shell has only one electron in it. Whatever that level is, the outermost one only has one. Okay? Your alkaline earths, oh, they don't show that. The noble gases they show in table 85. They have filled outer shells. Every one of them has an 8 in the outer shell. Okay? Now, let me show you something else. These groups down here, these are when you're filling your F no, they go right in here. Right after, you see, from lanthanum to here, you skip a bunch. 57, 58, 59, 60. Go all the way to 71, then pick back up. Just like the P's filled in here, the D's filled in here, the F's fill in between here and there. So all these things would be scooted over. You'd have a really long period, so they put them down here. These are called the rare earths. They're all really large atomic numbers, 58 and higher. So therefore you don't find them much. Rare earths, and note a few of these: thorium, uranium, plutonium. Sound pretty explosive, don't they? These are some highly radioactive materials. Americium is another. Many of these are. All these with parentheses are pretty radioactive. Okay? Hardly anything other than radioactive. Okay? So these they're rare, and their uses are fairly unique. One country in the world, to me, stands out with these, and that's the Congo in Africa. Congo in Africa is one of the richest countries in the world in terms of minerals. They have a lot of these things that nobody else has, but they're one of the poorest countries in the world. Part of that goes back to their colonization. Belgium took over the Congo as a colony and basically ripped them to shreds. What they did to the native population was just inhumane, and it's a sad, sad story of how evil mankind could be. So, and they've never recovered. They've been exploited by everyone who can get their hands on them, and they've never been able to come back and be what they could be. So it's rather a sad thing, but they have a lot of these rare earths. There is a nice little blurb in your book, fills almost half a page on page 222 on these rare earths. And I would say, take a look at this. You might find something that you find interesting and you want to follow up in a paper if you haven't already done one. The people behind the science, the guy who came up with this, a Russian scientist named Dmitry Mendeleev. Okay, he was the first one to really put together. Several have put together things sort of similar. Mendeleev put together the periodic table, so much so that where he had something that didn't fit, he would leave a blank. And guess what? Every blank that he left has been filled in. So he knew something would be there, they just hadn't discovered it yet. So rather than filling in the next thing, even though it didn't fit, he left a blank. And sure enough, they have filled in since then. Pretty incredible character. That would be another good paper topic if you haven't already chosen one. When we were talking here about your semiconductors, there's a blurb at the top of page 224. We talked about them some in the electrical chapter, but they talk about them more here. Top of page 224. There's another here about metals and charge we sort of talked about, and the outer orbitals. And that does finish the chapter. And we're right at we're not even at 3:45 yet. So we definitely do have time to do the lab today if you want to do it, and still have time to do your test. It's a paper lab. It's not going to take you that long. What we just talked about is going to be on it, so it'll be a lot fresher on your mind than if you wait till Tuesday, but we can wait till Tuesday either one. So which way you want to go on it? Do the lab or not? We've got plenty of time to do it and take your test, and you'll still be out of here early. Just not as early, but early. That means on Tuesday, all you have to do is your Chapter 8 test, the final exam, and then you eat pizza, Chapter 8 test, and then the final exam. Oh, did you hear that about pizza? Oh, yeah, you came in late. I forgot to tell you. Okay. Tuesday, we're going to have pizza. And so far, the class has asked for 3-meat pizza, pepperoni, and sausage. Have you got objection to those, or would you rather have some other option? Are you okay with that? You are? Okay. All right. All right. So, they're going to be Little Caesars, so it won't be super premium pizza, but it's still good pizza. Okay. All right. And other things I usually ask when people came in, I forgot to do you. Have you done student course evaluation? Okay, please do that before too late in the term. And I'll go over anything you have about what the schedule's going to be. So what y'all think? Before I say anything else, remember my famous lines? Nothing replaces reading the chapter. These slides don't cover everything. I don't cover everything. Nothing replaces reading the chapter. But once you have, there's a pretty good and fairly thorough summary, one of the longer ones, but there's just so much in here. The summary of equations is not super long, but it's more than most. The key terms are relatively large. Now, one thing the slides didn't show, and I should say this, Heisenberg uncertainty principle. It was in the text. I forgot to say it. I just happened to notice. A German scientist named Werner, I think Heisenberg, he came up with this thing. If you measure the location of a quantum object, meaning a very small object, if you can pinpoint the location, you know nothing about its momentum. If you pinpoint the momentum, you know nothing about its location. There is a certain degree of uncertainty. You cannot know everything about everything on the quantum level. It's just as impossible to do. That wasn't, it was in your text, but it wasn't on the slide set. I wanted to mention that too. Okay, applying the concepts, another great thing to study for your for the chapter test. 49 questions, which is a bit more than normal. Questions for thought, 12, that's about, or maybe a little less than normal. 6 for further analysis, they're pretty good. The parallel exercises would be more the calculations, but a bunch of these have your identifying the number of protons, neutrons, electrons, that kind of stuff. Really worth a look to see and pay attention to those. All right, and that does it for the thing. What did y'all decide? We want to go and knock out the lab today?
Sure.
Okay. I didn't know we were going to finish this, so I don't have the labs copied. So why don't you take a little break, and I'll run down and make copies. I think there's, what did I say, 22 of us? And I'll get the labs copied. Yeah, we'll stay in here. Unless there's some room you'd rather work in, but we don't need to be at a lab table.
You stay here?
Yeah. Pardon me?
Do you have the lab from Tuesday?
Yeah, but let me get it in a minute. I'm going to go make the copies first. I'll get it when y'all are in the lab. Got 3, I think. Oh, man. All right, I'm going to put this on pause. Okay. Looks like a fairly short lab, but it is going to take a little bit of time to do. There you have 4 atoms across the top of the page. carbon, magnesium, iron, and gold. Okay? I've written it in the electron number, mass number type thing that was in the book that we talked about last time, last Thursday when we started the chapter. So you should know what those numbers stand for. And your first two questions, number of protons, number of neutrons, comes directly from those numbers. Of course, number of electrons, what you're assuming they're neutral atoms, so that really also comes from that number, those numbers up there. Okay? The electron configuration, that's the stuff we did today. And you'll see pictures of it in the text. Things talked about it in the text. I pointed them out somewhere on the slide set, so you should be able to find some of those exactly in the text. Others you'll have to do a little more work on. Okay? Also, we talked about period, what that represents on the periodic table. Periodic table, that will be from there. The family will get off the periodic table. Whether it's a metal, non-metal, or semiconductor, we had some figures in the text and on your slides that was directly from. And the number of outer orbital electrons. Now, that's something that's a little maybe more vague, perhaps, but in the text, I want to point you to this. If you look at, on page 224 in your text, how many outer orbital electrons are found in an atom? And they mentioned 3 here. According to the list of elements, blah, 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 blah. Well, let's see, is that exactly what we were going? Okay. Basically, you look at the number on your periodic table. Remember they had Roman numeral numbers across the columns? That number will tell you what that number is. You have to know your Roman numeral numbers. That will tell you how many electrons are in the outer orbital. Okay? Any questions? This is a lab. You can work together. You can ask questions of each other. You can ask me questions. I'll be glad to try to answer something. I'd love for you to get good scores on this. So work together. Come up with what your answers are. Ask me if you have any doubt. Okay? All right. Okay, all those times I mentioned things that were going to happen Tuesday. One thing I forgot to say, while y'all are eating, and maybe I said it, while y'all are eating your pizza, I'm going to be returning all the labs and all the tests. So anything that has not been turned in by Tuesday, basically 1:15, 1:30, somewhere around in there, cannot accept it later. So if you have anything to turn in, get it done. Many of you, most of you have turned in most of your stuff. Fantastic. In fact, I'll be able to return some stuff today if I can get it graded, I think. But no, I know y'all need it for your archives. All right, okay. So beware of that. If it's not done by Tuesday, I can't accept it. Yes. I'll be here. No, I'll be on Birmingham campus tomorrow. Okay. What you can do is either slide it on the, can you go to Birmingham or you rather come here? Which?
I come Birmingham.
Okay. You know where Dr. Pruitt's office is? You don't. You know the B building?
Yeah.
You do know the B building. It's called the academic building. The end of the B building is closest to the baseball field, the tennis court, and the gym. When you come in that door from that way and come up that half flight of stairs, the top step, you're right there at Dr. Pruitt's office, out behind the secretaries in the copy room. So if you either give it to the secretary or ask for me, if I'm in a meeting, she'll take it and do something with it. So that'll be fine. No, it's too late. Sorry.
Oh, okay. That's good. That's good.
Oh, you need another? Yeah.
You said you was going to
What's that? All right, sorry, say it again.
I know.
Oh, no. Little Caesars. It's closer.
What's the period on MG? I got the first AT2A. So definitely just the final look over on. Okay. What's yours?
For carbon, I would say not.
What about these?
Well, what do those relate to?
For gold, that would be transitional metal because it's with the copper and silver.
Okay. Where did you get period 6? From the periodic table. Well, that's where the families are too.
So period is 6 and family is also 6.
Okay. Turn on the projector. Can you reach it? Okay. All right. Well, you can look at the slide.
Family columns.
Yeah. Okay. Here's you don't see the periods here. 1, 2, 3. The columns. There's the name of every column at the top. And by the way, Courtney.
So period is 1, 2, 3, 4, 5, 6.
What are you looking for?
Oh, 11. There's 11.
Where are you talking?
Family.
Which one are you talking about?
Gold.
Huh?
Gold.
Gold? Okay. Where do you see 11?
1, 2, 3, 4.
Okay,
5,
wait.
6, 7.
Okay.
Got 1, got
Wait.
2.
Look at the top of the column.
IA.
That's 1A.
1A, 2A, 3B,
So you want
4B, 5B, 6B, 7B, and then 8B, and 1B. What do I got? 1B?
I know, it's strange, but it is. There's where gold is. That's his column.
Okay.
Okay.
So that's the family is 1B?
Huh? The family, yeah. That's by the column. Now, Colby, Courtney, you're asking about, this is in your book too. You say carbon. Does that tell you what carbon is?
the metal?
Really? Where do you see that there?
It's right there.
Where is carbon?
Oh, I'm sorry.
Ah, yeah. Okay. Okay. Someone asked me about something they found off the internet, and it's true. What they do quite often in doing the electron configuration, they'll put one of the noble gases, the noble gas from the previous period, okay? And I don't know which one she was talking about. Let's just say it was iron. And what they did was the electron configuration for argon. That's what you had. And then they pick up from there and give the electron configuration from their own. That's sort of hard to figure if you're following your chart, but that's what that represents. So it's okay to give it that way, but it's going to be harder to figure out if you got it right or not. But yeah, you can't give it that way. Okay?